But I'm going to talk about the local register allocator project. So what's the local register allocator project? In brief, it's just another try to replace the local class. So far, that was a successful one.
It would be nice if you at least wouldn't talk if you had a rule.
If somebody doesn't know what is reload is most measure-dependent class in GCC. It's also a very important part of GCC register allocator. Reload exists in GCC since its day one. Actually, the same class with the same name was in the predecessor of GCC more than 25 years old. The design was taken from Pascal compiler. And unfortunately, during all these years, reload became very bloated, buggy, and very complicated part of the compiler. And just few people understand it well. If you look at this chart, you will see that reload was about 5,000 lines, source lines in first version of GCC, and it became more than 20,000 lines in fourth version of GCC.
Vlad, do you have, which architectures were added, which?
Yeah, probably, yeah. But new optimization was also added, like inheritance, which complicated a lot the load. So when I started this project, one of my motivation was simplification of the path for easy maintenance. As you know, reload has a lot of latent bugs. For example, probably about 1 year ago, we just fixed 9 years old bug in reload, and some bugs will be never fixed. One of them cannot find the register in the class. It happens when we use the first instruction scheduling before the register allocator. An introduction of register pressure sensitive instruction scheduling about 2 years ago decreased this probability, but still this bug exists. So one of my motivation was to simplify this path for easy maintenance. But my major motivation was implementation of new optimization, which is practically is not possible to do in reload because it's so complicated. Even if you implement a new optimization, it will make reload much more complex and much more buggy one. And it will require a lot of efforts too. What kind of optimization I wanted to implement? Of course, it's better speeding, not one by one case as in reload, but looking at the whole picture of necessary hard registers for reloads. Different splitting, which is absent in currently in reload, and it's very hard to implement. I just tried it once. Better inheritance, also inheritance not only basic block scope, but also beyond basic block scopes. Also splitting in the new register, new vector register, registers instead of memory. Sometimes it's profitable to do. And even bit-width-wise register allocator, that's allocation where we put several pseudo values in one very long register. And modern processor have a lot of such registers, maybe 256 bit. Sometimes it's profitable too. So what's wrong with reload approach? What it makes so complicated? This is just my point of view. Maybe have a different opinion. One of complication comes from the fact that reload is trying to do many things at once. Another complication is that reload uses additional data structures on the side of RTL. And actually reload works on this data structure mostly. And when it decides it's already done, at the very end, the reload rewrites RTL according to these data structures. And another thing, as most machine-dependent part of compiler reload is driven by so many machine-dependent hooks and macros. Although I believe that major source of information about instruction necessities needs should be instruction constraints from machine description. So when I started to design the local register allocator, I decided that it should be divided on small manageable passes, separated passes, more or less independent passes. Also, I decided that probably this is the most important decision, design decision. I decided that all transformation and all decisions should be reflected in RTL as much as possible. So RTL is changed during all work of local register allocator, and it's quite different from the reload approach. And again, I decided that instruction constraints should be primary source of the info about instruction needs. Any local register allocator major task is transform internal representation to satisfy all instruction and others constraints. And it could be done by several ways. There are two major approaches. One approach, I would call it split one pass approach, when we just go through all instruction, and when we need a register to satisfy instruction constraint, we just split the leaf range of pseudo assigned to this hard register and read it through this instruction. And it's done for one pass. If you look at a very good book, Bob Morgan's book, Building and Optimizing Compiler, he uses this approach. Another example would be IBM register allocator. If you look at Andrew McLeod's patent on this register allocator, you will see he uses the same approach. Andrew in this room, so if somebody wants to discuss his approach.
I don't remember anything from you.
Yeah, it was long ago, and more than 50 years ago, but still it's a pretty good approach. And another approach, I would call it spill iterated passes. When we need a hard register to satisfy the instruction constraint, we just spill, not splitting leaf range, we spill a pseudo living through instruction. And because we spill this pseudo other instruction in which this pseudo occurs, will have probably may have instruction constraints not satisfied anymore, and we do this check again and again. So we could pass several times through all instruction. And this is actually a classical example of this chatting bricks register allocator when we generate reload instruction and new reload pseudo shortening leaf ranges and repeat the global register allocation again in defaulted through several passes. We will have all instruction constraints satisfied. And actually reload is in some way simplified version of this approach. When we need a hard register, we just spill a pseudo-living through this instruction and repeat this process again. Actually, it's misleading, a bit misleading. I like more the second approach, the reload, because it's better fit with retargetable compilers, and GCC is, as you know, the most retargetable compiler these days. Also, on my experience, fields tends to generate smaller code, but still I should say that splitting can be profitable too, and therefore I implemented this different splitting in the local register allocator. So, in brief, how the local register allocator works. It goes through instruction, and when we need to satisfy instruction or this constraint, we generate a new reload instruction, we generate a new reload pseudo for this, and after such transformation, we actually do assignment. We assign hard register to new reload pseudos, and sometimes it needs to spill pseudos, not reload pseudos, leading through this instruction. And as we spill reload pseudo, we should repeat this process again. And when all instruction constraints are satisfied, we just change spill pseudo by memory on the stack, and because we generate new addresses, we need repeat and checking address constraints again and instruction constraints. And it looks like a pretty slow process because it's iterative. But I spent a lot of time to speed up this process. Actually, I decreased number of instruction process. I only process necessary instruction. Also, I worked very hard on the global representation. You could look at this as a cache, and it's always synchronized with RTL. I should underline this. It's synchronized. So this is block diagram of local register allocator. I just described the structure of local register allocator in brief, and we'll talk more detail about each pass. At the very beginning, we actually change scratches to pseudo, and this simplifies very much all implementation, because scratch is not nice. I think it's an additional thing. It's not necessary for local register allocator. And after that, I update virtual register displacement before actually checking all constraints. It's necessary to do because constraints should know its exact displacement. And after that, I run a constraint pass. We actually generate a new reload instruction and new reload pseudos. After that, there is a register assignment pass, which assign hard register to new generated reload pseudos. After the assignment pass, I run a memory comparison pass fast trend to remove moves involving rules build pseudo. And we should do this before constraint pass, because otherwise it will be break down by several instructions, and it will be very hard to remove it afterwards. Actually, it will be not removed by any subsequent pass after the loop. Therefore, I added this pass. And before register assignment pass, there is some transformation which focused on to implement inheritance and differential splitting. And if assignment pass was successful with accepting this transformation, they stay. If not, I just don't do this after the assignment pass. And we could do more such iteration. And when all the instruction constraints are satisfied, I change spill pseudo by real memory, and of course it generates new addresses and also extends stack and displacement change. And we need to do again this pass maybe one more time. And the very end, I just change the rest of pseudo by hard register. All the rest of pseudos assigned hard registers. This is this is slide about how I work with scratches. As I told, I changed scratches by pseudo, and they are spilled at the beginning of Local Register Allocator. It's important for simplification or implementation. There is example of instruction needs scratches, and you see the last alternative of this instruction required that scratch should get hard register. And if you use the last alternative of instruction, then pseudo corresponding to the scratch will get hard register and will stay. If we use other alternatives, the pseudo corresponding to scratch will be spilled, and at the end of the Local Register Allocator, I change spill pseudo by scratch pseudo by scratches itself.
So you recover the stack slot at that time?
No, I don't assign stack slots for scratches. It's not necessary because it will be removed. So there is no worry about some optimal properties. Updating virtual registers. You know, RTL uses a lot of references to virtual register. Virtual register, it could be a frame pointer or argument pointer, and it denotes the virtual register denotes some real hard register in displacement. For example, it denotes a real hard frame pointer plus some displacement, or stack pointer plus some displacement. Unfortunately, offsets may change every time when we extend stacks, and we don't know the final displacement until the end of Local Register Allocator. Therefore, I use approach. Actually, I always update displacement. So at any time of Local Register Allocator, we just can change virtual register by corresponding hard register with zero displacement, and we will have the right code. And such approach needs a few changes in the rest of this compiler, because some standard predicates and operand constraint does not recognize virtual registers as area of hard registers. But fortunately, this change is so small. The most complicated and biggest part of constraint pass. This pass actually do RTL transformation, generate new reload construction if it's necessary, and generate new reload pseudos. Sometimes it's also substitute pseudos by the equivalences if it's profitable. There are a lot of tons of details how does it work, and actually, but I should mention here only about reload pseudo because it's a new notion. There is no such thing in reload and GCC. When we have matching constraint, in other words, we need to put in the same place output operand and one input operand. I just use one reload pseudo for this usually, but sometimes it's not possible. For example, operand modes are different, but they should be in the same register. So in this case, I generate two reload pseudos and mark them bound. Bound means that these pseudos got always the same allocation, the same hard register or the same memory. Also, this pass mimicking form reload pass in alternative tuning. And why is that? If somebody wrote machine description or did or ported GCC, he knows that when you write machine description, you should actually keep in mind how reload looks. Other approaches would be required a lot of rewriting in machine description. Pseudo assignment pass. There is no any change, no any code transformation in this pass. We just assign hard registers to reload pseudos to really satisfy constraints, and we always should be successful with this. And this is achieved by several techniques. Most important technique is spinning other pseudos for this. And after some spinning, we actually could assign hard register for non-reload pseudos. Sometimes it's possible. And there is a new notion I introduced for the local register allocator. It's called register bank. By default, there is only one register bank. But for x86 and x86, I defined several of them. But I could say for this presentation two register banks. One registers which need rex prefix and one register which doesn't need. If we use usually the first level heuristic for choosing hard register is based on cost, but when the cost is the same, I use hard register from smaller register bank. And why is that? Because for this definition, x86, it results in smaller plot size.
Isn't that similar to the existing regular quarter?
There is, but it's not always, this sort of not always corresponds to what I said. Therefore, I identified this.
I don't understand why there's non-reload pseudos at this point.
Non-reloads, there is no hard register substitution yet. So we have non-reload pseudos from the beginning. Some of them assigned to hard register already by Local Register Allocator. Some of them still by the Local Register Allocator. And new pseudos
Those that existed before it was started was no LRA was not. LRA creates new supervisions.
I thought IRA was going to handle
No, LRA driven by Global Register Allocator decision. So we have before Local Register Allocator already assigned to all pseudos, and we generate during Local Register Allocator only real pseudos. And we spill original pseudos, which existed before the Local Register, no pseudos, to assign hard register to real pseudos. And I use for assignment pass to find conflicts, I call them leaf ranges. It's analog. There is analogous thing in Global Register Allocator. IRA. Somebody look at this, it's familiar. So pseudo 193 is program point from 64 to 77 and from 2 to 5. I skip probably because it's late. Inheritance. As I told before the assignment pass, I do some transformation to achieve inheritance. For example, we have spilled pseudo P, and we need to generate reload instruction in the new reload P1 for some instruction, and later for the other instruction we need again to generate new reload instruction in new reload P1. And I add new pseudo and assign this pseudo reload P1 and then reuse this. And this pseudo before assignment pass actually spilled. If and I should sell it short leaf range for this pseudo. And if assignment pass assign new P hard register, we have a better code. And if it doesn't update assignment pass, I just undo this transformation. And I should say inheritance is done in extended basic code scope. It's different from reload. Actually, I tried a global approach, but it didn't work well. It's very slow, but there is practically no visual performance at all. And it's understandable because this new P should be short leaf, should have a short leaf range in order to be assigned, to get a good chance to be assigned to hard register. Leaf range splitting is done on the same path as inheritance, and it's done not only pseudos but also for hard registers. And because it's done for hard registers, we will have no anymore, as I told, one which will be never fixed in reload. And I do transformation. I generate a new pseudo S for new hard register R or a new pseudo to assign hard register. And I assign the same hard register to this new pseudo S. And if assignment pass spill this new pseudo S, we will have reference splitting. If it doesn't, if it stays in the same hard register, done for extended basic blocks. And this also simplifies implementation of polar space optimization. So it's done the same mechanism by replacement.
I think there is any benefit from polar safe if the splitting is done intelligently. I mean, it's conceptually the same as just having a stack slot and having it.
Yeah, it's the same as in the current polar savers, but it's much more understandable implementation. Also, it's not hard to understand polar saver, current polar saver, but it's smaller and more nice implementation. And actually, it's done by product of this implementation. Spills, it's pretty easy. We just extend stacks and assign pseudos to different stack slots. We minimize stack slots, number of stack slots for this, and because we generated new addresses and displacement can be changed, we actually need to run a constraint pass again.
So, do you update the displacement for the virtual registers at this point immediately?
No, as I thought, it's done right before constraint pass. So, but because we need to run constraint pass, it's done again. Okay, this is internal representation. I should talk a bit about this. Because I work on RTL, and RTL is always changed. We need very frequently information about instruction constraints, and all other things, operands and so on. And just accessing RTL is very slow because it's Lisp-like representation. There is pointer chasing. It's very, very slow. So in the first implementation, I tried data flow infrastructure for this, but unfortunately, it makes implementation pretty fast. I mean, faster than just using RTL and instruction record for instruction. But still, it makes all compiler 10% slower than compiler with reload, which is not acceptable. Therefore, I worked a lot of internal representation for specialized internal representation for Local Register Allocator, and my design goal was to minimize footprint of this internal representation. There is a static part of instruction description common for all instructions with the same code, and minimal dynamic part for each instruction. And there is also some structures for information about pseudos. I already mentioned diff ranges. There is also important information, actually build set of instruction identifiers difficulties where this pseudo, in what instruction the pseudo actually occurs. And with this internal representation, I achieve the same speed as reload, and sometimes it's a lot better speed than reload. So what's the current state of this project? I created a branch last spring for this, so it's public. Anybody can try this. Local Register Allocator is switched on by default on this branch. source code of Local Register Allocator is 70% of real source code, although I implemented a lot of new optimization. So, and it's better divided by files. Practically any class have implemented in all file. So it's has a lot of, has a good structure. Formats. Actually, I tried this before merging on last week, so maybe the data are different now. And for Power 7, they which somebody happened last 6 months since my last work. So I need to look at this. There is more than 2% improvement for spec FP 2000 on latest Ivy Bridge processor. Why spec FP? Because Local Register Allocator is important for big basic blocks, and usually floating point benchmarks have very big basic blocks. So it's just the same that the Local Register Allocator is doing variety. Code size changes. It's another sign that Local Register Allocator is doing the right thing. You see there is more than 2% improvement in code size, and average code size for spec FP 2000. Actually, sometimes they achieve 3% in average for some key AMD, for example, has even better code, more code size increase. Speed. I usually use a very big benchmark. It's 500 million lines of code for floating point cost for Fortran 90, and you see there is practically 3% speed up for x86 and 32-bit more for this benchmark. There is even an improvement for Power 7 64-bit, but I should say it's hard to compete with reload because reload doesn't work with it. And if you look at the number of instructions, for example, Valkyrie, you will see that Local Register Allocator uses more instructions than reload. But because probably because of better locality and because we generate probably less instruction for x86, we have this speed up. For Power 7, sometimes reload is still faster, but the difference I didn't see that reload faster than 1% on Power 7. But for x86, didn't see on latest processor that reload is faster. Local Register Allocator always faster. And this is actually an important slide
for the performance. What is with O0? Optimization.
No, it's minus 03.
With our optimization, what the number?
I didn't try this. I'm interested in more optimizations. No, I am an optimization guy. Yeah, I should try this. I agree. Maybe it's not so rosy. And I will try. It's a good point.
We spilled a lot with.
This is how merge should be done. Actually, I'm planning to merge this over GCC before my next spring. I think because it's this disruptive patch, I think it should be done on the first day of stage 1 or first days of stage 1. And we could do it differently. for platforms I already mentioned, which this bootstrap works. But my experience shows that there's a pretty big work to work a new target to local register allocator.
What's the type of
you never know. For example, the most complicated target is PowerPC, I should say. They use so many tricks, and it took the biggest time to port local register allocator to PowerPC.
Were the changes required in the local register allocator?
Not only local register allocator, in machine dependent part. But I should say, sometimes you just switch off all tools used by real. For example, for HTTP, you just switch it off. And that means that we would remove a lot of code after we remove reloads from machine dependent files.
I think the second one is definitely what we want to end up with when we release these.
Do you think it's
So I suppose at the beginning we should just force all targets to use the new one to make things actually look at what happens in the fix at the beginning of stage 1.
You know,
Because we can always go back for the
Yeah.
well, it didn't work out. But
Yeah.
I mean,
Richard, I understand there is always advantages and disadvantages. Disadvantage that probably some targets will be broken for release if we remove the rules. Alright.
You know what, I think what they're discussing is don't remove reload to start, but start change the default. for
Yeah,
all
that's
targets.
what I'm proposing. It's more realistic approach.
But our goal should simply be to remove reload by the time of release.
Yeah, sure. It's my goal actually. And
Right.
then yes.
You can make functions zero.
If everything is in place in waveforms, can you reuse Diego's matrix over targets to get people to fill it in? It's
Yeah.
kind of a social thing there.
Yeah.
It entices people.
David.
Yeah, two quick questions. One, have you tried it with any of the more unusual embedded architectures like the SH5, I mean any of these? Jordan Saban architecture. Have you tried whether?
Yeah, the first I tried on real hardware. As you see, all these platforms I can find hardware on this, and actually I use this. I'm going